Welcome to the Deep Dive. We're here to break down complex math concepts, fast-tracking you to understanding. Today, we are diving into Hilbert space. It's quite an elegant idea, really. It takes the geometry we know, our familiar 3D world, and stretches it, well, way beyond that, into infinite dimensions. So our mission today, let's unpack its definition, trace back its kind of surprising history, and then look at where it actually pops up. You might be surprised it's everywhere from quantum mechanics to, believe it or not, how we see color. Ready to explore a space unlike any you've probably thought about before.
Hmm.
Okay, let's get into it. Think about, vectors in regular 3D space. We have this intuitive sense of length and the angle between lines, and that all comes down to something called the dot product, right?
Exactly. The dot product gives us those geometric notions.
So the genius of Hilbert space, it seems, is taking that core idea and just generalizing it, like asking, can we still talk about distance and angles even if we have, like, infinite directions?
That's precisely the spirit. Formally speaking, a Hilbert space is a real or complex inner product space that's also complete. Now, don't get lost in the terms. The inner product part, that's just the grown-up version of the dot product. It's the rule book for defining length and angle in these bigger, more abstract spaces.
Okay, the inner product handles the geometry part. What about completeness?
Right. Completeness is absolutely key. Think of it like this. If you have a sequence of points that are getting closer and closer together, like they should be heading towards some specific point, well, completeness guarantees that limiting point actually exists within the space itself. It means there are no weird gaps or missing points. Calculus works reliably there. It's actually a special kind of Banach space, but it's the inner product that gives it that extra geometric flavor.
Okay, so completeness gives us the mathematical confidence, sort of, that our calculations won't just fall into some kind of void.
Exactly. It provides that essential analytical rigor.
And what's amazing is, even way out there, in potentially infinite dimensions, basic geometric rules we know, like the Pythagorean theorem, they still hold, like exact versions.
They do. The Pythagorean theorem, the parallelogram law, they have perfect analogs. It shows a really deep consistency in the mathematical structure. It's quite beautiful, actually.
Wow. Okay, so where did this powerful idea even come from? It sounds pretty abstract.
Well, it didn't just appear fully formed, as you might guess. Its roots go back to the early 20th century. People like David Hilbert and his student Erhard Schmidt, they were working on something called integral equations. And they noticed that for certain types of functions, specifically square integrable ones, you could define something very much like an inner product.
Which let them talk about functions being perpendicular or orthogonal.
Precisely. At roughly the same time, you had Henri Lebesgue developing his theory of integration.
Ah, the Lebesgue integral. That really broadened the kinds of functions mathematicians could handle rigorously, didn't it?
It did. And that turned out to be crucial, because then Frigyes Rees and Ernst Fischer, working independently, proved something vital. They showed that this space of square Lebesgue integrable functions, we call it L-Lud, wasn't just an inner product space, it was also complete.
Ah, so that was the piece that connected the geometry from the inner product with the analytical reliability of completeness.
Exactly, the missing link. And then later, John von Neumann came along. He really formalized the whole concept, gave it the name Hilbert space in honor of Hilbert, provided the first complete axiomatic definition. And perhaps most famously, he applied it directly to quantum mechanics. It became the mathematical foundation for describing the quantum world.
What a journey. From solving equations to describing fundamental reality. So let's talk about that. What does this abstract math do for us? Where does it make a difference?
Oh, the applications are incredibly wide-ranging. The most well-known is definitely quantum mechanics. Instead of picturing quantum particles like tiny balls, we represent their possible states as vectors in a Hilbert space. The weirdness of quantum mechanics, like superposition being in multiple states at once, fits naturally into this vector framework.
So the math itself sort of encodes the probabilities.
In a sense, yes. And things we measure, like energy or position, those become operators that act on these state vectors. It's the language of quantum theory.
Okay, that's huge, but it goes beyond just the quantum realm.
Absolutely. Take Fourier analysis, breaking down a complex sound or image into simpler waves.
Like musical notes or sine waves.
Exactly. Hilbert spaces provide the perfect setting because these fundamental waves act like an orthogonal basis, kind of like perpendicular axes in our 3D space, but potentially infinitely many. It makes signal processing incredibly powerful. We also rely on them heavily for solving partial differential equations. These are equations that model things like heat flow or fluid dynamics or electromagnetism. Hilbert spaces, especially Sobolev spaces, let us find weak solutions. when exact ones are impossible.
Okay, and I read something fascinating connecting this to our everyday experience. Something about color perception. That seems like a leap.
It does, but it's a fantastic example. Think about all the possible physical colors, the actual combinations of light wavelengths. It's an infinite spectrum, essentially an infinite dimensional Hilbert space. But our eyes only have three types of cone cells, right? So our visual system performs this incredible trick. It maps that infinite dimensional reality down to the 3D space of colors we actually perceive.
Whoa, so that's why completely different mixtures of light can sometimes look identical to us, that medamerism thing.
That's exactly it. Our brain is effectively projecting this vast Hilbert space of physical light onto a much simpler 3D Euclidean space. It's data compression happening in real time inside our heads.
That is genuinely mind-bending. To think that this abstract structure, cooked up over a century ago to deal with equations, is now fundamental to understanding the subatomic world and how we literally see the world around us, it really makes you wonder, doesn't it? What other hidden mathematical structures might be out there quietly governing parts of our reality that we just haven't managed to fully unpack yet?